Click the bell icon to get latest videos from Ekeeda.
Hello friends, this is a video from chapter 7 to understand color image processing. So we have gone through the understanding of color fundamentals first of all, the various color models, and now the two major portions of color image processing. We are covered with pseudo color image processing, and we have also addressed how exactly the full color image processing works. Now it is time to understand the transformations of color into this particular domain. So let us begin with the topic. So here we can start for the color transformations in color image processing. So color transformations actually deal with processing the components of the color image within the context of the single color model, as opposed to the conversion of those components between the models. So here the models are like the RGB to HSI conversion or HSI to RGB conversion. So these are the transformations. Now we can have the formulation into this particular topic. We model the color transformations using the expression. So the expression is very simple. It is representing G of xy obtained while operating the original image represented by f of xy by the operator capital T here. So here f of xy is the color input image, we can say. G of xy is the transformed or the processed color output image, and capital T is the operator onto the f over the spatial neighborhood represented into the span of the x comma y here. The pixel values here are actually the triplets or the quarters, that is the groups of 3 or 4 values, we can say, from the color space chosen to represent the images. We will restrict our attention to the color transformations of the form represented by the equation, where we have onto the left hand side small s suffix I, and it is obtained by having the computations of capital T suffix I over the bracket involves R1 comma R2 up to R suffix n here, where small I ranges from 1 to up to small n here. So here we can simply represent G of xy, that is obtained in the form of S1 to Sn, and that is from f of xy representing f1 to fn here. So this is the transformation operator here, T1 to Tn here. For the notational simplicity, Ri and Si, the I is in the suffix, actually are variables that denote the color components of f of x comma y and g of x comma y at any point representing x and y here. The n here is the number of components, and T suffix I is the set of transformation or color mapping junctions, we can say, that actually operate onto the Ri to produce the Si that we have represented on LHS. The n transformations Ti combine to implement the single transformation function, that is capital T here. The color space chosen to describe the pixels of f and g determines the value of n. If the RGB color space is selected in this case, for example, we shall be having small n is equal to 3. Therefore, we shall have R1, R2, R3, that is denoting the red, green and blue components of the input image respectively. If on the another example we have CMYK model or HSI color spaces, so the corresponding values of n shall be initially for 4 for CMYK, and for HSI it will be 3 again. Figure A that we are going to visualize here, that actually shows a high resolution color image of the bowl of strawberries and a cup of coffee. So this was actually digitized from a large format, and it has the dimensions of 4 inch by 5 inch color negative. So let us visualize a full color image and its various color space components. So here this is the figure part A, full color image, and here we have can, magenta, yellow, black, red, green, blue, hue, saturation and intensity components. So any of the color space components in this figure can be used in the conjunction with the equation at the second place we have shown. In theory, any transformation can be performed in any color model. In practice, however, some operations are better suited for specific models. For a given transformation, the cost of converting between the representations must be factored into a decision regarding the color space in which to implement it. So we wish here to modify the intensity of the image into the figure A, that true color image we have shown onto the right hand side. So using the representation of the equation g of xy is equal to k operated onto f of xy here, where this k ranges between 0 to 1. So 0 less than k, k less than 1 here. So HSI color space, here we have intensity representing S3 is equal to k times R3. Here we can note that the transform to HSI requires complex operations, and if you take the case of RGB color space, for each RGB components we can in general represent S suffix I is equal to k times R suffix I here. And if it is the case of another color model representing CMY color space, so that time for each CMY component we have SI as a outcome computed by K operated over Ri added with the second term we have 1 minus K here. So here we have this figure. This is actually adjusting the intensity of an image using color transformations. So part A is the original image that we have already shown you in the earlier figure also, and part B here it is the result of decreasing its values by 30%, that is letting the k is equal to 0.7. so 100% we consider 1, decrease or reduction by 30% it will yield 70%. And from C, D, E here the required RGB, CMY and HSI transformation functions are represented here. So I is actually the intensity component separately representing other than the hue and saturation. H and S for hue and saturation, I for intensity. These two models are represented in only two portions here. Now the transformations of this type are among the simplest and most used color processing tools that can be carried out on per component basis also. Now we have color complement. Here in this case the hues directly opposite one another onto the color circle. The next figure we can show you, that is color complements here. Our interest here is in the complements that stems from the fact that they are analogous to grayscale negatives. As in the grayscale case, the color complements are used for enhancing the details that is embedded into the dark regions of the color image, particularly when the regions are dominant in the size. So here complements onto the color circle we can see. So we can have can, green, yellow, red, magenta and blue here. So the complements we can have onto these opposite sides in this particular fashion. Now the next figure we are going to have, that is A and C portion that show the image from the earlier figure A and its color complements. The RGB transformation used to compute the complement are plotted into the figure B. So there shall be a sequence figure A, B and figure C here. So let us have the visualization, and the nomenclature is here. So this is representing the color complement transformation. This is part A, original image that already we have shown. This is part B, complement transformation function representations for here RGB. Here we have separate for H representing hue, S representing saturation, I representing intensity. The portion C is the result here. It is actually the complement of figure A and it is based on the RGB mapping function. So this is the function which is responsible to get this kind of resultant output image. And the part D is the approximation of the RGB complement using the HSI transformations shown here, H, S and I here. The computed complement is reminiscent of conventional photographic color film negatives. So reds of the original image are replaced by cans in the color complement. When the original image is black, the complement is white and so on it will go. Each of the hues in the complement image can be predicted from the original image using color circle that just now we have shown, and each of the RGB component transforms involved in the computation of the complement is a function of only the corresponding input color complement. Now we have color slicing here. Highlighting a specific range of colors in the image is useful for separating objects from their surroundings. The basic idea is either to have first of all the display of colors of interest so that they stand out from the background, or we have the second reason, that is to use the region defined by the colors as a mask for further processing. One of the simplest way to slice a color image is to map the colors outside same range of interest to a non-prominent neutral color here. If the colors of interest are enclosed by a cube or hypercube where we have n greater than 3 and representation of width by capital W and centered at a prototypical, for example average, that is prototypical color with the components represented by A1, A2 up to AN here. The necessary set of transformation is given by, here we have the representation S suffix I opting the value 0.5 if the condition satisfied is mod of Rj minus Aj is greater than the ratio W by 2, and here we can have at the suffix any j, that is ranging between 1 to n, here I is 1 to up to n here. If this condition is false, that time the assignment to Si will be simply R suffix I as it is. These transformations actually highlight the colors around the prototype by forcing all other colors to the midpoint of the reference color space. For the RGB color space, for example, a suitable neutral point is middle gray or color. So here we can represent the values for the middleness 0.5, 0.5 and 0.5 here. If a sphere is used to specify the colors of interest, so in that case the equation can be modified like this. Si shall be opting the value 0.5 if the condition is the summation for j is equal to 1 to n in the bracket Ri minus Aj squared shall be greater than R naught square here. So I is the same 1 to up to n. If it is not satisfied as like the before, we shall assign Si by simply R suffix I here. So here R naught, R suffix 0 representation in the formula is the radius of the enclosing sphere, or in the case of hypersphere we have n greater than 3, and here we have corresponding representations A1, A2 up to AN. These are the components of its center, that is the prototypical color. So now this was the input image represented into the full color. Now here we have the representation with the help of cube, with the help of spheres. So the information for color slicing transformations that actually detects in the part A, we can say that the reds with the RGB cube of the width W given by 0.2549 centered at, we have the three values 0.6863, 0.1608 and 0.1922. Now for this particular image onto the right hand side part B here, reds with the RGB sphere of radius 0.1765 centered at the same point is taken. The pixels outside the cube and the sphere were replaced by the color, that is midpoint 0.5, 0.5, 0.5 here. Now the figures A and B here actually show the result of applying both the transformations. In each case, a prototype red with the RGB color coordinate that just now we have said here at the diagram was selected from the most prominent strawberry. W and R were chosen so that the highlighted region would not expand to undesirable portions of the image. The actual values, that is W is equal to 0.2549 and 0.1765 were determined interactively. Now we have another subtopic here, that is tone and color corrections here. The focus of the current discussion on the most common uses, that is photo enhancement and color reproduction, is here with the tone and color corrections. The figure we have here that shows the typical transformations used for correcting three common tonal imbalances, that are flat, light and dark images. So here the tonal corrections for flat color images, adjusting the red, green and blue components equally does not alter the image hues here. So this can be represented. So this is for the flatness and this is the image obtained by correctness. The function of RGB can be represented with the help of this particular graph. So now the tonal corrections for the light, that is actually the high key color image. So here also the adjustment of red, green and blue components equally does not alter the image hues here. So this is for the lightness, and after correction we obtained here the resultant image shown in this particular portion, and the function responsible for this correction is represented in RGB components like this. Now we have the third one, that is tonal corrections for the dark, representing the low key color images. So here this is the dark image, the input. After correction we get this output for the image sample, and the responsible function is having this particular nature, opposite to the previous one we have shown on to the earlier slide. Although color imbalances can be determined objectively by analyzing with a color spectrometer, a known color in an image, accurate visual assessments are possible when white areas where the RGB or another model, that is CMY, or you take CMYK components, should be equal are present. So color balancing corrections for CMYK color images we can show. So this is the original corrected image. So for here we have the resultant, the color balancing corrections for the same model. So here this particular image has this function representation, that is heavy in blackness. If we make the weakness into the black color, the representation of the function here and the output image will be like this. If the heaviness into the can component is there, as this is the first component of this particular color model, we get the visualization of the image like this, and the function for the C component will be this way. On the other hand, on the weakness of the can here, the resultant image shall look like this. Now if it is the case of magenta, the heaviness shall give us the resultant image like this with this particular function. Here M represents the magenta. If the magenta on the other hand has this particular nature, it has the differences into the visualization for the output image like this as you compare these two. And for the yellow component, the third component in CMYK here, so here the heaviness will be having this particular curvature into the function representation resulting image, and corresponding weakness into the function shall have this resultant image here. Now there is another approach for color transformation, that is histogram processing. The gray level histogram processing transformations can be applied to the color images in an automated way. We have already covered the histogram equalization, simple histogram processing for the grayscale images. Since the color images are composed of multiple components, however, consideration must be given to adapting the grayscale technique to more than one component and or the histogram. It is generally unwise to histogram equalize the components of the color image independently. The reason is that it results into the erroneous color. A more logical approach is to spread the color intensities uniformly, leaving the colors themselves, for example hues, that are unchanged. Now we are having a visualization of the figure. The part A shows a color image of caster stand containing the cruets and shakers whose intensity components span the entire, that is normalized range of possible values between 0 to 1 here. In the part C of the same figure, we shall see a histogram equalization of the intensity component without altering the hue and saturation component, resulting image that we see here. And figure B, the middle portion we see here, that shows the intensity histogram of the new image as well as the intensity transformation used to equalize the intensity component. So histogram equalization followed by saturation adjustment in the HSI color space we can see here. So this was part A, B, C, D here, representations of functions of hue, saturation and I here are. So this is the histogram before processing, and this is histogram after processing that we obtain, and the corresponding results are also the visualizations here. Although the intensity equalization process did not alter the values of the hue and saturation of the image, it did impact the overall color perceptions we can see. The figure D, the last portion, that shows the result of correcting this partially by increasing the image saturation component subsequent to the histogram equalization using the transformation that we have shown the function into the part B on right hand side upper. This type of adjustment that is commonly when working with the intensity component into the HSI space, because changes into the intensity usually affect a relative appearance of colors in an image. So I hope the color transformations are very much clear to you people. By the next lecture, we shall address the topic color image smoothing in the color image processing here. So if you like the videos and want some more information onto the subject digital image processing, you can subscribe to Ekeeda channel. Thank you.